It's a great honor for me to be here, meeting so many friends that I haven't seen for quite a while, and also, being back in Ann Arbor, getting the energy, the Ann Arbor energy that we miss as a family. My neighbors are here from times past, and some people that I spend a lot of time with and I learned a lot from. And so I want to thank you for being here and coming to this lecture today. Yesterday, I spent quite a lot of time with students, and I miss that too from time to time. Probably the most exciting thing I'll tell you about the students, the first time I was there for a launch of a spacecraft. I'm the person who signs off and basically says, let's go. I'm also the person who is prepared to give two speeches, the one I want to give and the one I have to give if something goes wrong. So just the day before the launch, I met all the managers and the leaders of that particular spacecraft, which is the next generation weather forecast spacecraft of the United States, the first of them. And 6 of the managers of instruments and subsystems thereof were my former students, right from here. And some of them right from Ann Arbor. And yes, exactly. I did not know that. But what happened is that has become a pattern and frankly drives everybody crazy because I always, at the top of the pyramid, understand what's happening right there at the instruments because I can pick up the phone and call one of my former students. I want to talk about the shore of the cosmic ocean, and of course, many of you understand, let's see, I'm trying to learn the technology here. So this one is not working. So many of you, of course, know where that is a quote of. There's a quote out of what I think of as a philosopher, really a thought leader for science, a person who has inspired me throughout my career, Carl Sagan, who said, "The surface of the Earth is the shore of the cosmic ocean. On this shore, we've learned most of what we know. Recently, we've waded a little way out, maybe ankle deep, and the water seems inviting." Research that I'm going to talk to you about, recent results of research, many of the results that I'm going to talk to you about are results we just learned. And what I want to tell you, though, is this is research from that ankle-deep water. Most of what needs to be known in this universe remains hidden from us. The universe, including the Earth, is full of secrets that remain to be discovered. And the excitement that I have together with the team, is to unlock those secrets and kind of open up the world in which we live and think. Exploration unites. When we landed on Mars just last year, front page articles around the world carried that above the fold, including the New York Times and the Washington Post. What's equally exciting to me is the newspaper run by the religious leadership of the country of Iran also had it above the fold. So did China. So did newspapers around the world. Exploration, the human activity of exploration, understanding nature better, doing amazing things together, matters today even more so than the past. And that's what I want to talk to you about in this talk. The motivation, learning about nature, but also the excitement of doing this work together with many partners and doing things that really transcends what's there. I need one more sign error. Now we're good. All right. So science at NASA is about 3 topics. discover the secrets of the universe. I just talked to you about that. Entrepreneurship is a word that's not often used in this room in introductions of speakers in physics. Many of the innovations here at the university and elsewhere have led to companies, have led to economic value. But even if that did not happen in the first 10 years, the first 20 years of research, we would still do it. Because discovering the secrets of the universe is moving us forward in a way that if actually look back in history, that some of the biggest transformations of what we do, how we live today, what creates value, comes from that very activity. We will, whenever there's an opportunity, take that opportunity and turn it into value with the various tools that are being developed on this campus and elsewhere. But by itself, discovering the secrets of the universe is absolutely worth it. One of the topics that is really at the center of our research in a multitude of disciplines is finding life elsewhere. You know, of course, that this is a topic that has been with us for millennia. Philosophers wrote about it, taught in other buildings on this central campus. About this topic, some religious leaders even talked about it. For the first time in history, we can address that question about life elsewhere with the tools of science. And I want to talk to you about that. And then the third one, in many ways, is the most important one for us. It's protecting and improving life on Earth. I already talked about one way we improve life on Earth because of the value that comes from these innovations, sometimes in very unexpected ways. All of a sudden, there's a whole industry growing. All of a sudden, new jobs are being generated here and elsewhere. But there's other ways, and that is related to, for example, the fact that 80% of the data that goes into your weather forecast today comes from space. 80% of the data product. We did not think that would be of relevance the first time we went to space. But it is. There's many other ways space matters today and creates value protection from space weather, rocks that are hurled towards us for the first time in history. We see them coming, and we're learning how to deflect them. And basically, in a topic we call planetary defense, that is also in our disciplines. Those are the topics we're dealing with. That's another way of looking at the science discipline. Every one of those are words, and no, I'm not going to talk about all of them, are missions that we're currently working on. The ones in regular fund are in flight, around 20 around the Earth. You see some good old friends kind of in astrophysics at the top left, like the Hubble Space Telescope and others. You also see, of course, at the bottom there, the overall exploration of the planets. Every book around the world that has images of planets, with very, very, very few exceptions, have images from these missions that are on this chart, and missions that used to be on this chart before the mission ended. And then, of course, we have missions that look at space around the Earth and looking at our sun. I want to point to the top right corner, where the oldest spacecraft are hanging out. And the oldest spacecraft are called the Voyagers. They're going to come back in this talk. The Voyagers have been with my life forever. When I was 8, my godfather gave me a book in German. It's actually not great a book, but it was a book about space exploration. And I read it. In there was the description of how we're going to build these spacecraft and launch them, the Voyagers. And it's still in my office right now at NASA headquarters. And if you ever visit me, I'll show it to you. I used to have it in my office here at the University of Michigan. And the reason I'm bringing that book along is, first of all, it means everything to me. But secondly, it does matter that we talk about science. It does matter that we put it in books, we put it in podcasts, on Twitter. We mention it in our classrooms. We talk about it on the plane, the person next to you, who let them sleep afterwards. But it is important to talk about it, because the opportunities that come from an education that I was fortunate to get in a public setting, like this university, is changing lives and creating opportunity that are beyond the things of dreams. So I want to take you on a journey on this jour of our cosmic ocean and talk to you about a few things. And of course, I will start with the Earth. This is an unusual picture from the Earth because you see something in the foreground. And of course, what it is a picture taken from the moon with the Lunar Reconnaissance Orbiter. Just when it came from behind the moon, it took a picture of the Earth with its camera that's usually pointed down and looking at the surface of the moon. It's mapping out that celestial body, just like every other body, worthy of discovery. But you look at the Earth, and we remember, of course, the quote of the Apollo 9 astronaut who said, "I went out there to discover space, but what I did is I discovered the Earth." In many ways, one of the most important benefits of going to space is understanding our own planet. Talk without electricity. Our own home, that is, of course, a planet that, of course, is very much linked to our destiny, and a destiny we're also affecting ourselves with how we live on this planet. So this is what we see here. This is a picture of one of missions. Actually, it's a bunch of pictures. And of 2018, and it's pictures from an Earth science mission. The Earth science mission took a picture of this storm. Now, this picture is highly personal to me. Right underneath this storm is my father-in-law during that time. He lives in St. Croix, and basically the storms were barreling over them. Now, I want to tell you, the big story of last hurricane season, there's always devastation. There's always agony. We cannot deflect those storms that are coming our way. But the big story of the last hurricane season is every single hurricane trajectory of the last season was predicted at an accuracy like never before, and the rainfall associated with it, which, as you know, is the most important reason for death in a hurricane, was predicted as well. And so why is that? Because of the research tools that are out there, because of a community, including the community in this university and elsewhere, that learns about this and actually protects and improves life for my father-in-law and all of the people there, including us. I want to talk about two areas that we're adding a lot of value to, and this one is a mission. We're going in and out here. The Soil Moisture Active Passive mission, which is a mission that is actively sensing the emissions of the emissions of water and kind of the sensing the interactions of water with microwave emissions below the surface. Around the United States, we now know what these where the droughts are, how the water at the bottom of plants, of course, which will affect, without doubt, farming and so forth, how that is evolving over time. This is one of those snapshots. But if we go through, we of course learn that this is changing. The big drought of California is in one instant the story that makes the news. The lack of water in the Midwest last year, for example, in some of the areas, are other stories in which we, on a regular basis, add value to farming communities, add values to people that depend on that information and allow them to farm smarter, to actually help with the management of water in a way that protects what they're doing. I want to talk about the polar regions. And I want to talk about a mission that we just launched. It's called IceSat II. Now, the polar regions are really far away from us, but they affect our lives in a direct fashion. You've read in the news that the ice is melting, especially at the North Pole. This one is the other end of the Earth, the South Pole. Perhaps what you don't read as much is that there's a lot of stuff we're discovering right now. Data point. 2 to 3 years ago, the accuracy of forecast of downfall in a season, precipitation in a season over the Antarctic, was only known within a factor of 2. We're getting better. But it's not true that we know every one of those things. It's also true that from our data, we believe that until just 2 or 3 years ago, some of the regions in the Antarctic actually grew in ice, where of course on the net they melted in some other parts. But the accuracy of that needs to be data-driven. We're not a policy shop at all. We want the data so we understand the secrets of the universe related to our Earth. In this case, it affects us. If I had a beachfront property, which I don't, they don't pay enough at the government. If I had a beachfront property, I would care about that, as well as all the industry that relates to that. This matters. Okay, so what we have done is we've launched a spacecraft that is currently in orbit, and it's orbiting in a polar orbit every 40 minutes. It's flying over the Earth. And it shoots 10,000 times a red laser down per second, 10,000 times per second, a red laser down, and actually measures the reflected signal coming back. Over ice, there's a lot of reflected signal, but we have enough sensitivity that we can even do it over plants. And I should have brought a picture of Michigan, but not as important in this case as this one. This is only 3 weeks of data, and we're doing this all the time. And this is, in accuracy, by far, the most important measurement of the volume of ice in the Antarctic right now. The accuracy of this, before we had the mission, was about 100 yards, like a football field in the horizontal dimension, was a few inches in a vertical dimension. The accuracy of this in a horizontal dimension is 1 meter, 1 yard, is 3 millimeters in the other dimension, like this. We will learn from this about this important problem, this important part of our world, by measuring and learning how to do this. This was really hard to do. It's hard to launch lasers. It's super hard because everything has to, if you have ever played with a laser in a lab, it's really hard to align those things. Well, now launch them and shake them, and then turn them on, and that's what we're doing. As we're stepping away from the Earth, we're going to look at the sun, our star. Our sun is the Rosetta Stone of all stars. Whatever if you learn about stars, most stars, there's a few really strange things, like neutron stars, and we have not learned that at the sun. And you should be glad. It's not healthy to be. But basically how a star is built, what the processes are at the center, how a star affects its atmosphere, and how that atmosphere affects its environment, we learned at our own sun. And our sun, of course, is a really exciting star, a variable star. In fact, the sun is weaker today than when you were born. I don't care how old you are. It's getting weaker a little bit. And that's not unusual if you go over history. Every once in a while, the sun got stronger, and it got weaker. It became more active. The sun is really wimpy right now. The magnetic field of the sun, which is one of the quantities in which the sun it projects its energy, is down about a quarter since 15 years. The sun is a variable star. And of course, we actually don't understand how that works. And we built a mission to encounter the sun. And I want to tell you, this morning I got an email that confirmed that not only did we just finish the close pass of the sun, but we did so successfully and in full health. I told in a class yesterday, I just got an email that says we got through, but I now know everything went perfectly. It's really hard. Now let's talk about football again. We're in Michigan, right? So, and there's always hope. If the distance between the Earth and the sun is a football field, we're going to the 4-yard line. Now, if you've ever been camping, you realize that the heat that you get goes with distance. Roughly, if it's radiation alone, 1 over distance squared. So we go from 100 to 4 yards. There's kind of a factor of 20 times squared. That's 400, right? So that's how much more heat we have to take to do this. But what we're doing is we're flying through that atmosphere as a star. We're making measurements. There's that we believe is, as I said, kind of quintessential measurements to understand every star in environments, especially planetary environments there. And we do it for the first time right now, yesterday. So that mission, by the way, is named after a guy who's still alive. Every once in a while, it's important to break rules. We never did this before, and we broke the rule. Gene Parker, Michigan State grad, not just good in basketball. Gene Parker is a guy who looked at the sun, a theoretical astrophysicist, looked at the sun and said, hey, in his 20s, if you look at the temperature of the sun and you look at the comet tails, you realize that the sun is blowing out its atmosphere. Otherwise, the tails would not point away from the sun. And he basically wrote down a theory that says that not only does it do that sometimes, it does it all the time, and it does it in a supersonic fashion. Like a Laval nozzle of a jet, that physics, but at the sun in all dimensions. He wrote that down, and he got fired over it. It was too crazy. Are you kidding me? The sun is losing its, why would it do it? Like, in fact, he says he got 2 referee reports. The nicer one said, the author should go to the library before he starts talking. And I remember sitting next to him. He's now 91 years old. Sitting next to him at lunch with his family. And his family in tears because, I mean, you know there's a lot of Nobel Prize winners. There's one person on Earth that has a mission named after him. And sending a cool mission to a hot place like this. And so basically, we launched, and I said, how does it feel, Gene? And he came over and said, that was really great. When are the data coming? So that's the first thing he said. Second thing, basically later, he gave this, and he's a gentleman, like, you know, like people talk about the Midwest, that's who he is, just the nicest, kindest person to everybody. And so after his TV interview, a famous man around the world, he just was invited to Jeff Bezos' place, you know, just incredible guy in his 90s. Basically, he said, Thomas, I came there, you know, we're done with all the cameras off. It's like, I wish these bastards were still alive to see this. Where this emission of the solar wind that Parker predicted, of course, affects our environment. And of course, we have a magnetic field at Earth. We think that magnetic field is really important for how our atmosphere evolved. Mars does not have a magnetic field. And we know that it loses its atmosphere. We measured that 2 years ago for the first time, at the speed of which Mars loses its atmosphere. The Earth has an atmosphere. Now, what happens, though, is the magnetic field is an incomplete shield because the magnetic field from the sun that's carried out with the solar wind, the magnetic field that we're measuring here on Earth, they interact in a complex fashion. And what we do is we have a mission, I would think of them as the Blue Angels in space. 4 spacecraft flying information to measure that process in which the magnetic field gets cracked open. A fundamental process that also is important next to neutron stars. It's important at other planets. It's important all over, including in lab plasmas, perhaps for fusion as well as we go forward. That process, we measured for the first time, the 3-dimensional structure and its temporal evolution. That process we discovered in the last 3 years. For the first time, after it being hypothesized by, guess who? Gene Parker. Later on. In fact, I went, when I did that speech to name after the mission, I looked at how many missions in that portfolio of 100 or so that are related to the publications that Gene wrote. 35 is the answer. So just an incredible, incredible man. So, of course, we're on the space station with people for 18 years. So those of you who are younger than 18 years, your entire life we've been in space. And we've learned how to live and work up in space. And we're eager to go deeper into space. But in space, we've learned a lot about the environment and the interactions of these particles as they go down into aurora, an important indication. At my introduction, he talked about northern Michigan. I love that part of the state, just incredibly beautiful. And that's in part the reason for it, too. It's a lot closer to the northern lights because, of course, the other way would be all the way south, but kind of closer to the pole. That incomplete protection that I just talked about, that reconnection actually cracks open that shield a little bit, and particles come in and get accelerated and end up in the polar regions and light up the atmosphere with the beauty that is there. If you've seen it, think of that. For the first time, that process we've discovered. I want to talk about education a little bit. I'm a strong believer in the fact that the motivation of doing science and the excitement of doing science should not be just in universities. It's great that a talk like this is given to a public. That's why I showed up, because I believe in it so much. But what I also believe is that actually the public can be very much involved in doing research. And the research of aurora is a really good example. We discovered a new type of aurora because of public participants, citizen scientists, actually actively measuring from wherever their locations are, whether they're in Marquette, Ishpeming, up there in Traverse City or in Ann Arbor, and the equivalent around Norway, and everywhere, and get those data in. We discovered a new type of aurora through the process of citizen science. In fact, I believe in it so much that in a budget proposal that I just submitted, we actually create a citizen science line to actually enhance those kind of interactions. I believe that the science is the realm of all of us, not just those of us who are professionals in science. I want to talk about Mercury. I spent a lot of time at Mercury. This is Mercury as imaged by the Messenger spacecraft with an instrument on board that was built right here at the University of Michigan. And we went there and we discovered this planet, and we thought when we went there it's kind of a dead rock. It's an active, geologically active place that is out there, a place that has a magnetic field just like the Earth, unexpectedly so. And a place that is full of secrets. In fact, the European Bepi Colombo mission just set its course. Yesterday it was announced towards towards planet Mercury with a high propulsion engine technology that's being led out of Ann Arbor in the Gallimore lab towards this exciting planet again. And we talk about it a lot in the future. I want to talk about Mars, though. Together with Mercury and the Earth and Venus, one of the terrestrial planets. Now, the most important thing when you look about planets is to recognize that planets change. So, a few billion years ago, if somebody gave a talk here, yes, that would look different. 3 billion years ago, if I put this up, most of the northern hemisphere would be an ocean. Not a deep ocean, 150 meters deep. There would be streams on there and river deltas. There would be an atmosphere that's a lot more similar to the Earth, and probably there was a magnetic field at Mars. What I just told you is totally contradicting everything I learned in my classes on astrophysics. Science is about learning, not about restating facts. We learned that by the missions we did. We learn about Mars. There are some things that are different. Actually, we have no clue why Mars changed. It could be that they got hit from the outside. Mercury, we think, got hit too. We think the moon was knocked out of the Earth. So collisions, cosmic collisions, as part of early solar system dynamics. This could have been a reason. It could also be that it happened from the inside. And I'm going to talk to you about a mission for the first time we're looking on the inside of this. Now, there are other things that are really different, and that is, for example, that there's no continental plates on Mars. So what happens if there's a hotspot, a volcanic eruption at Earth, a few million years, there's always another island that comes out. Do you remember Hawaii, right? Kind of a hotspot that came up. Right now the hotspot is under the Big Island. Fascinating, absolutely incredible. Well, if you're on Mars, there's the volcano, and every time there's an eruption, it's at the same place. That's why the largest volcano in the solar system that we're aware of is on Mars, because it always hit the same spot. Mount Olympus is that place. So we know some things are similar. We know some things are different. We know this place was a lot more similar than we thought. Now, the exciting question that I'm going to get back to is, during that time, when there was water there, when there was an atmosphere, when the temperature was a lot more balanced and it looked less some kind of Nevada scene, if you take an image, during that time, on Earth, the first life formed in similar conditions. And we can't wait to figure out whether that also happened on Mars. At this moment in time, I have no clue what the answer is to that question. But I do know that the pieces that you need to get there are being discovered one by one. And I'm going to talk to you about that in just a minute. This is Crisp Crater. When I went to school, Mars was dry. They told us Mars was dry. Really smart professors, by the way, well-meaning. So we'll look at Crisp Crater. It was done, an image taken by our orbiter. And you see these gullies there, these black gullies coming off the Crisp Crater. What's interesting, and I didn't bring the movie, but what's interesting, those gullies change as a function of time. In fact, there are things on Earth that look just the same way. When the sun hits it, it thaws, for example, in Utah, and mud comes down the mountain range. That's what's happening there. By the way, we're still arguing whether that's the right explanation. Most people would believe that that is. Somebody said there's another explanation out there that it talks more about instabilities that are generated by different kind of properties of viscosity of the dust and so forth. Science is not about certainty. Science is about doubt. And that's also on this. But the point is, the surface is changing on a day and week-to-week basis at Mars. If you go look at it today, it's different than yesterday. And that's exciting. We thought of it as this thing that was there forever. Part of this is because of this courageous mission that we said goodbye to just a few weeks ago. I always said I've been to funerals that were less sad than that last meeting with this team, where we said goodbye to Spirit and Opportunity. Spirit, of course, we had lost for a while. Opportunity was killed off by Mars. It was killed off by a dust storm that created such a dark sky that the solar panels that you see hanging from the left and the right in these flat panels did not have enough power to sustain its life. We thought we could save it, but the clouds were too dark, we know now, and basically it froze to death up on the surface, which is the right way to die, by the way, if you're a robot. So it shouldn't be because of some bureaucrat like me saying you're done. So the numbers of that exploration is incredible, considering the fact that the mission duration that we designed it for was 90 days. Look at that. I'm like, if we ever achieve that way, again, that is a miracle, right? By the way, the reason the mission duration, it's not that we over-designed it. We got the Mars environment wrong. Remember, Mars killed off this, I just told you. Well, Mars also kept it alive. So the storms we got a really severe one that killed it off. The storms actually blew off the dust off the solar panels. And so the reason it was going to die after 90 days is because it was going to accumulate all that dust. Well, it blew it off. And so it got rejuvenated all the time during the storm season. And so it lived for a long, long time. This is the last set of data that it took in the environment. It is now sitting and as a testament of exploration. And hopefully, young people here will see pictures of others on Mars like them finding it, or perhaps their children. So this is really exciting. Curiosity rover is right up there. And this is a selfie, so it has an arm. Sticks the arm out, literally, and takes a picture. And Curiosity is all about understanding these building blocks for life. Curiosity, Spirit and Opportunity told us about the water nature of the environment. Curiosity is the next step. What are the places, what is the make and the composition of the places there? And this is a scene around Curiosity, and this is Gale Crater. Now, if you look at Curiosity, I always said that you can do a really good puzzle that basically says, is this on Earth or on Mars, right? I would bet this is on Earth, right? Except there's no VW van in the back there. That's usually in this scene, right? Somebody out there enjoying the desert. But you see, of course, you know immediately what this is. Now, we know it's right. There used to be water standing there. It dried off. This was shaped by water. In fact, we're going to go back in 2020 with a mission and go back there. Actually, in this environment, we took probes, and what we found are organics, complex organics that were sitting in that ground. The limitation of these measurements are our own instruments. It's not nature. We did not expect organics that complex. In fact, in the classes that I referred to, we were told that making these organics is really hard. They're everywhere, even in comets. Glycine is on comets. We're going to go back to that river delta. We're going to land there and actually collect samples, and then in another mission that we're going to launch in 26, we're going to go there and pick up the samples and bring them back. That will be the first round trip to the red planet we've ever done. Round trip of historic proportions, and there's probably 5 miracles we have to achieve till then, including launching off another planet. We've never done that. It's much harder than launching off the moon. The planet is much heavier, and the rocket needs to survive night before it can go. No technology we have today can do that. The Europeans are also going with a US instrument. This is an instrument that is the next generation. Built in the United States. This instrument's MoMA is the next generation detector for life kind of building blocks. And so that's what we're going to look at with this. And that's the Mars story. Again, the story of Mars is the story of a changing planet. A planet where the miracles, the secrets of the universe are being discovered right now at the level that we would have never expected even 10 years ago. And so that story keeps on giving. Just really exciting to go forward. Which celestial body is this? Just shout out. Second? Pluto. That's right. Pluto was a mission that, the mission to Pluto New Horizons was a mission that had a really hard time getting funded because the scientists were so convinced that it's boring. And it went to Pluto, and what we found, of course, is we knew, is that we had a body with an atmosphere that is freezing out because of the fact that the orbit has eccentricities, more like an ellipse, less like a circle. And what happened, we found there, and we saw oceans of liquid nitrogen, of methane. We saw active geology. We saw a body that in its own world is both beautiful and complex at a level we did not understand. These bodies out there, tens of thousands of them, are bodies that right now we're trying to understand, because those bodies from Pluto and beyond are bodies that are, in fact, the building blocks of the solar system. This is another body. It's called Bennu. We're in orbit around it. This is the smallest body any spacecraft has ever been in orbit around. It's 500 meters in diameter, and it's kind of a gravel yard in 3 dimensions, right? It's kind of early pieces there. There's a lot of water on it. Remember that class I talked to you about? No water in those things. They were really sure. There's a lot of water in it. You know what's also interesting? At the polar region at the south, at the bottom there, South Pole, I don't know why I should call it that. It's a small rock rotating. Anyway, at the South Pole, it's shooting out ice cubes. Frankly, we were for a while, we were worried about it. So they're not supposed to be active. Why is this thing active? You look at nature, you see surprise. You look at nature, you'll learn. You look at Bennu, you learn about active asteroids. We know they're active asteroids, but these things that are active, aren't they comets? That's why they have tails, right? Well, okay, you know, the two families, asteroids and comets, they used to be very distinct, not so much in nature. So that's what we're learning right now. By the way, because it's such a small gravity, everything is slow. So these things, even if they're in an ice cube coming our way as a spacecraft, we can easily take it. You know, so it's not like, you know, a guy throwing an ice cube at your left eye across the room. So it's not that kind of impact. It's much more channel. So we're good spacecraft-wise. But what we're going to do, in fact, is explore this body, and then in 22, we're going to grab material and bring it back to Earth, and then bring it to our labs, because we can't wait to see what's in this thing. It's already surprised us so much, we're going to go beyond it. Beginning of the year, actually on January 1st, that's where I spend my New Year's Eve, is flying by this guy. And that's with the same spacecraft, New Horizons, that flew by Pluto. It kept on flying, and we directed it a little bit to go by this little body, a Kuiper-Belt object. Those are the building blocks of the outer solar system. I'm going to play it again. First of all, it's two blocks. And if you look at the composition, it's more like fruit salad, less like a smoothie. So in other words, there's little pieces of different materials that were coalescing around it. And when we did that image, by the way, it's hard to find that thing. You know, it's so far away, putting your camera the right way to actually find it. The big challenge there was kind of the speech that I was ready for this one, is we didn't see it. Because you really need to point the camera the right way. There's a whole bunch of research that's motivated by understanding these bodies at the outer solar system. The MU 141969, or Ultima Thule, we've nicknamed it, that is out there, a snowman that's out in space, and kind of telling us about the beginning of accretion, the part that basically says the beginning of how these planets get baked in, at the interface of gravity and kind of coalescence of these dust grains and then bodies of that type. This is tiny, a tiny object we flew by, and we're learning a lot of work. We're coming to as we go step out, we're coming to towards the end of the sphere of influence of the sun. And actually a little bit beyond. This is the Voyager spacecraft. Remember I told you about in my book. The Voyager spacecraft is out of that sphere of influence of the sun. And the reason you know is that these curves, you see they're kind of flatter, and then all of a sudden there's a step, both in blue and in red. One is Voyager 1, blue, Voyager 2, the one behind it that did all the Uranus and Neptune encounters. And it stepped down. It's out there in the depth of space, far away, and is in galactic environment, immersed in galactic gas, and it's on its way. So I want to quickly, before I go to astrophysics, I want to talk a little bit about distance. And do you want to join me up here? She's amazing, by the way, preparing everything. Hey. So I don't know how to talk about distance, but I know how to talk about time in this. So basically what you're going to do is you're going to stand there on your spot. That is the sun. Do you see that sphere she has in her hand? The sphere is the size of the sun in some scale. Do you see that little thing? It's about as big as I could afford a diamond on my wife's wedding ring when I was a postdoc. So it's tiny. That's the Earth in the right sphere. So the shore of the cosmic ocean is on here. Over there is the sun. And frankly, sorry, how are you doing? This is the distance. See how tiny? Tiny, tiny. Sun is over there. Okay, now let's talk. Thank you so much. This is where we live. Everything you've ever loved. Everybody is on that little pearl. The light that's taking off from the sun at the speed of light takes between 8 and 9 minutes to come to us. 8 or 9 minutes, I was at the beginning of Mars, right? So the light took off. It's now here. Voyager 1, that I just talked to you about, and it's up there, is right now 20 hours and 5 minutes away from us. Remember where you were yesterday morning, just when you woke up. That's when light, a signal from Voyager 1 took off. That's just arriving right now on one of our antennas. By the way, it's agonizing if something goes wrong. And you say, do this. Light goes out goes out. It's like, do it, send back. 20.5 plus 20.5, 40, 41 hours later, it says, I did it, now what? So, what I'm going to talk about, the closest of it, the closest star, just like the sun, is 4.2 years. If I flew Voyager at the speed it got there, you know, from the 70s to where it is right now, to that star, to Alpha's sun, it would go another 10,000 years before it gets there. But it's still at the shore of the cosmic ocean where we're making these discoveries. Because we now know that for every star in a galaxy, on the average, there's a planet out there that remains to be discovered. In 95, before 95 where I did these classes, the answer was, theoretically, there should be planets. Probably 10% of the stars may have them, but we don't really know. 95 was the first announcement of 2 planets. Immediately attacked by everybody because they were planets, none of which exists here. They were Jupiter-like planets at Mercury distances. There are a lot of theories that said that cannot exist. It's really hard to learn about nature if you have n equals 1, one example to study, one solar system. It's really hard to learn about solar systems. We're learning a lot about solar systems now. It's really hard to learn about life if you have n equals 1 to study. And we still don't know what's important about what makes life and what's not, because that's what we're learning right now. So I want to talk about this, and basically what I want to talk about is a record of which is going to break. This is, as of April 2nd, the number of confirmed exoplanets right now, most of them by our observations, and we're going to break 4,000 in just a few weeks. Probably it's 2 weeks, I would say, we're going to break 4,000. You can go look at yourself. There's another 3.4 thousand NASA candidates. There's systems. Planets don't hang out alone. There's many planets, just like ours. That's very normal, and we learn about this. And frankly, what I want to talk to you now is how we do this, and I'm going to ask you to come back up again. And what we're doing right now is we're using this very technique that you're going to demonstrate, and that is that we have light, very accurate light, looking at stars, and what happens when a planet gets in front of it. Show us what happens. You can first go close to the sensor, so it's easier to see the effect, of course. So a slight dent in light that is there, and you see that dent because of the light is very stable and the detector is very stable. What's much more realistic is a pass that's much closer to it. And you see it's a very tiny dent. And you see the noise up there. It's getting closer to that noise. Now imagine being in deep space, looking at that star. You need to develop really, really accurate sensors to do that very thing. And it's that very activity, very simple, that we finally can do the right way. And basically that has kind of uncovered this. So it's that technology that uncovered that understanding at the level that we've never seen before. So what I want to do now is, and of course what I just explained to you in visual form is this one. And so it's great that we find those planets. In fact, we have a dozen or so what we call Earth-like lands. We have no clue what that means. I'll tell you what we say when we mean it. Those are planets that are at the right place. So water, if it was on the surface, we believe could pool on the surface. So in other words, it's not too hot for everything to evaporate like Mercury, and it's not too cold for everything to be frozen solid like Pluto. or other planets. It's right there in that Goldilocks zone, just good enough. Now what do we want to do, of course? It's going to be a while until we can visit those. I just convinced you with my little demonstration. But what we want to do is learn how to measure their atmospheres. See, the light that comes from these planets that we're detecting with the TESS spacecraft, we're staring into the sky and looking at these, and we're investigating the closest such planets to our environment because we can't wait to go follow up with them to look at the atmospheres. And so here are some of those planets that are there. Of course, visuals, these visuals, we don't know what they look like, but some of them, they're liquid lava. If we know the materials that are there, at the temperatures that they're at, lava balls that are flying around. Some of them are more like ice balls or cold, things like this. Some of them have some time variability. So we already know, we think we have the first moon that is there. And basically, what we have learned is kind of statistically, with correcting for all the biases, here's what we've learned about the abundance of planets. So here is what science does to you if you explore. Remember, at Earth, we have two types of planets. Terrestrial type planets that are rocky, then these gaseous big ones. The most abundant planet type in the galaxy is a type of planet we have none of here, which are super-Earths and mini-Neptunes. So things that are rocky, but way bigger than they should be, and things that we have no clue what these others are. So we're starting to develop that, and what we can't wait to start doing is looking at their atmosphere. The atmosphere of Earth changed because of life. Life is important for the planet. When bacteria started taking over the environment, the atmosphere changed. Methane was there. All of a sudden became important, other molecules. So I want to talk to you like how we're going to do that. And of course, the atmosphere, as the little planet flies in front of the star, does what you're going to demonstrate with this particular device that you have there. That's basically subtracting out certain lines out of the light that is coming from the star. Now, these glasses are amazing. Remember, we always talk about football here. So now think about this. You're at a football game, a night game. Do you see those lights up there? Imagine there's a lightning bug 2-3 inches next to it, and it's farting. That absorption we want to detect. The atmosphere is tiny compared to everything there, and the emissions of the planet is tiny compared to emission of the star. So we need to learn how to blend out the star very, very accurately and measure the absorption very, very accurately. How do we do that? We have two technologies that we're working on and we're investing in, but at this moment in time, I don't know how. We have never done it. What we have done in some of these bigger planets with the Hubble Space Telescope, as they fly through, we have enough accuracy that we have measured the first few atmospheric technologies, just the way you showed right here, Monica. That way, we've done the first measurements, like a handful or a couple handful of planets. But the exciting ones are the ones that look a little bit more similar to the place where we live, again, at the shore of the cosmic ocean. All this stuff I just told you about, these first measurements, are only years old. And we can't wait to work on this. The telescope that we're going to do is a telescope that this morning the bus is in thermal vacuum, and we're closing the door, and hopefully it will go just the way we hope, and we will launch it in 21. It's the James Webb telescope, the most complex telescope ever built, to do just that, the first measurements. By the way, when it was designed, we did not know about these planets. So it's a lucky coincidence that there will be good measurements from that. And of course, nature sometimes is good to you. I want to tell you a story at the end, a story of exploration that has more a human touch. Exploration, besides the fact that it's important, it's exciting, it teaches us about nature by itself, it's important. It's an experience that is worth spending your life on. And that's what I want to explain to you. I want to go look at InSight, which is the first robotic geologist at the surface of Mars right now. I want to tell you about landing on Mars. Landing on the moon is basically learning about where you are and using rockets, little boosters, good enough that you touch down at low speed. Landing on the Earth is basically coming in with high speed, having a good thermal protection system, and the Earth will slow you down to subsonic speed, then you put a parachute out and you bump into water. Landing on Mars is hell, because it's neither of those. It's a little bit of both. You cannot ignore the atmosphere, which is now 5% of the Earth's atmosphere, because if you do so, you will burn up. In fact, it will slow you down, but never to subsonic speeds. You cannot, of course, you still have to, look at the floor, at the ground. And so what you have to do is come in and basically let things slow you down, then put a new parachute out, which is very different than any parachute we've ever built, which is a supersonic parachute. You then want to blow off the bottom, that heat shield, because you need a clear view of the ground. And then you want to go sense where you are with camera and lasers. Then you want to touch down. And that all has to be autonomous, because the light is too slow for you to joystick it. Everything has to work perfectly to do that. And the only problem was on this one, it has to work at the backside of Mars, as seen from the Earth. So you're agonizing over it. This is so hard that 50% of the landings ever attempted by humanity have not worked. In other words, they made a crater, not a mission. You don't want to be in the business of crater making. So what we did for that is we put, to actually have eyes on the ball, we put a new type of spacecraft out that was developed brief size scale, CubeSats they're called. They were invented in 2000. Everybody thought they're garbage because they're too small. How would you ever be able to do something with those? Well, the answer is they're essential for landing on Mars. Those two spacecraft, by the way, led by a Michigan grad. I'm going to show them to you with a black shirt, Andy Klesch. He sat in my classroom years ago, right here. They were flying by Mars, and they were looking at the signal coming up and sending it back to Earth. It's really hard to fly those things. In fact, we've never flown them, but we learned how to fly them so well that we actually knew their position more accurately than the position of the spacecraft itself. That's how good these kids were. And that's how they look next to the team of the others that ran the spacecraft. So what I want to talk to you about is the team that sat there. Now, needless to say, remember my speeches? I have the good speech and the bad speech. In this case, the speech is a lot worse because you don't know. Like if something explodes on the pad, you're pretty sure it's not going to work, right? You see the smoke and everything. Not here. You may have no data. So Andy and his team were really important. Now, what happened? Within 24 hours before we actually went in, we lost one of the CubeSats for 6 hours. These CubeSats were a little bit more finicky. The first time we do things, they're not as robust. That's good. That's why we built two. We knew that. Well, the second one kind of picked up some problems too, so I started to get nervous, and one guy saw me, and I'm a hardware guy, so I built things, right? So basically, the director of the lab said, let's go to a meeting. So see these people there? They sat in that room in their sandals in California, right? Next to me was a guy called Gentrilli. He was being at the center of every landing from the Vikings. So he's, the age of my parents. Sharp, incredibly sharp. Around the table It's a diverse set of specialists who are best in the world at what they do. And together we looked at data. We looked at data, and we realized we're coming in long. So by looking at pulsars in the back of the spacecraft that is beeping at us, we realized are a little bit off from where we thought we would be. We're a little bit too far. So what we need to do, if we just went in that way, we would get out of the area that we really analyzed carefully. So we knew every rock. So we knew it's a good area. So we get into a place we don't know so well. So the question is, what do we do? Of course, what you never want to do is do a big maneuver and then go in with an ill-defined state because something went bad. So the team around the table was looking at data and arguing about this. All I did is sat there, and I loved it. Because the best people in the world were arguing with each other of what the best solution is. That's what exploration is about. It's not one guy doing this, not Gentry. My former student, she sat in my classroom before, argued with him about something, and I think she was right. Because she's better at that particular thing than he was. Together we made the decision, they made the decision. I'm all hands off at this point, because I do not add any value. This is not what I do. We made the decision to actually turn the spacecraft around, boost, pull it in, turn around, come down. And so what happened next is what I'm going to show.
Marco Alpha, Marco Bravo, maintain lock status.
Altitude convergence, the radar has locked on the ground.
Yes.
Radar locked.
Standing by for lander separation. Lander separation commanded. Altitude 600 meters. Altitude 400
Every
meters.
signal comes through the CubeSat.
200 meters. 80 meters. 60 meters. 30 meters.
That's horrible.
20 meters. 17 meters. Standing by for touchdown. Touchdown confirmed.
Exploration is hard. Exploration unites, and exploration teaches us about our shore of the cosmic oceans. This is the last picture one of those CubeSats took as it flew by Mars. You see Mars and you see its antenna that it used to pipe the data back, done by a briefcase-sized spacecraft sent back to Earth, making history with the ingenuity of the type of people that are there. This is Bruce, who did that work for 20 years. His entire career was at the balance that moment going in. It's people like him, the courage that comes from exploration, the support that we're getting from you, the support we're getting from others in the United States that allow us to do this. And it's now on the surface. This device now on the surface, inside is on the surface. This is a selfie minus the arm that was edited out of this deployed. It's a solar panel powered spacecraft on the surface of Mars, and out there is now the first instrument placed by a robotic arm on a planetary surface, which is a seismometer that is now waiting for the first Mars quakes. We think they're there. So far we haven't heard it yet. There's one that almost looked like it. The people are arguing. I don't think it's one at this moment in time. We're waiting for it. We will for sure remain to be surprised. This is what we're imagining. In 2020, we're going to launch a spacecraft with the first rotorcraft, first controlled flight in a different world, a helicopter that are going to go there. Our hope is in 30s we will investigate, explore that world with humans on the surface. We want to explore, we want to push the envelope, we want to move forward. It's incredible what we can do, the ingenuity that brings us there will bring all the value back to Earth and it will give us more understanding of our cosmic ocean here at Mars, about ourselves and the world around us. Thank you so much.